Oh, okay, sure. Okay. All right. Let's get started. So may I know who sitting here are still on the waiting list at this point? You are? Okay. I think we are now safe to put everybody, on the registration, but I need to double check the numbers. Because look at the seat, I think roughly the sizes matches the upper limit. Okay. Second question is that, so you can see there is a videotaping crew there, and we've posted already the video of the first two lectures. Has anybody looked at the videos? Not yet? Okay. How do you feel? Are they satisfactory or?
I actually missed the two lectures, so they were really helpful.
Oh, okay. Good. Okay. I hope that wouldn't encourage people to miss more lectures. All right. Okay, so let's get started. So last lecture, we actually talked about, as we said, okay, so there are two types of graphic models. One is a directed graphic model. The other is an undirected graphic model. And in last lecture, we pretty much covered the semantics and the representational kind of formality of directed graphic model. In particular, we spent some time covering the kind of statistical independence statements encoded in the graphic model. And today we are going to do the same for the undirected graphic model so that we can wrap up the representation and move on with other more interesting parts. Just a quick review. Here are some definitions I summarized from the previous lecture so that you need to remember. First of all, we must understand that every graph, if we use it as a backbone for a graphic model, then this graph encodes a set of independent statements or properties, which can be summarized like this, right? So X is a set of random variable, Z is another set. These two sets are conditionally independent given Y if Y deseparates X from Z. And we have definitions about deseparation, if you remember. It is defined on a moralized ancestral graph, and we have some algorithms to detect that without resorting to an ancestral graph, right? And also we defined, another more rigorous correspondence between a graph and a distribution, which is called a IMAP. Basically, a graph is an IMAP of a distribution if the independencies encoded in the graph is always a subset of the independencies in the distribution. Okay, this is the way you relate a graph to a distribution. And usually, the distribution can be richer than the graph because actually we will see two ways of getting richer. One is what you already see. It's like we can always play with the numbers to artificially create some independencies in the distribution, which may not be apparent in the graph, right? And the other is what we will see today very soon, that there are some dependencies or some independencies in the graph which are intrinsically not encodable by a particular type of graph. And we will see a few examples today. And here are some small tests of your understanding of the IMAP. For example, a complete graph, which means there are no independencies in the graph, represents a IMAP of any distribution, right? And if you have an empty graph, then you have all sorts of possible independencies, and it should be the superset of all graphical model in terms of independencies. And then, of course, we have this concept called the minimum IMAP, because you can have many IMAP of a distribution to the point that you can have a complete graph also as an IMAP. Then what's the point of using the concept IMAP? Well, the really important concept is the so-called minimum IMAP, which gives you the best possible match between a graph and a distribution, so that when you show people a graph instead of a numerical or symbolic distribution, people have an easier life in decoding or digesting or extracting the independencies out of a graph, out of a graphical model. And remember, there can be several different IMAP or minimum IMAP because there is something called I equivalence, which I didn't really say a lot last time, but you should probably, if you read the assignment material, you should be clear about what I meant, right? So for example, different graph can actually encode the same set of conditional independencies, right? For example, let me give you this: A independent of C given B. What could be the graph that actually capture this particular conditional independence? Okay, let me suggest one. There should be a cascade like this, right? But what about this? This gives you the same type of conditional independence. Therefore, these two graphs is I equivalent. They are I equivalent. Do we have another one? Make B the common ancestor, right? So this is also an I equivalent graph. That's why you may have multiple different graphs encoding the same set of independencies. And that's exactly why sometimes learning a graph based on data using certain principle may not be scientifically very informative. Why? Because based on a statistically defined loss function, such as a likelihood defined on a distribution like this, you will get this same thing equally likely. And which one is correct, you don't know. Therefore, if you try to interpret the scientific meaning or the semantic meaning between random variables, you may not get the right one, or there isn't maybe a right one at all from data. Right? So this is the controversial part that actually hurts the practice of learning graphic models. And we will talk about this issue later even more. All right, so that's the very quick review of what we covered last time. And now let's move to a new domain, okay? So there are some cases we probably, ideally we want really something called a perfect map, in which the dependencies encoded in the graph is going to be the same as the one encoded in a distribution, right? But that's not always possible, as we can guess. For example, in fact, there are limitations in certain representations, such as a direct graph model, for which some of the distribution, some of the independencies can never be represented. So here I give you an example. For example, I have these two probabilistic independent statements, right? We have 4 random variables, A, B, C, D, and I say I want to build a distribution, or there is such a distribution in which A is independent of C given B and D, and B is independent of D given A and C. Okay? And now let's ask, is there a Bayesian network that can actually capture this? Right? We can always build such a distribution by playing some trick. We can carefully design the numbers in this 4-variable table, or using some other ways. But let's first make sure that we examine whether Bayesian network is such a representation, or direct graph model is such a representation which can encode this. So 4 variables, you can imagine different ways of connecting 4, and here are 2. What are the independencies in here, in this graph? If you can tell. So I think it's safe to claim that A independent of C given B and D. That's probably safe to claim, because these 2 things indeed separates this one from this one, right? And do we have actually B independent of D given C and A? Why yes and why no? When C is given, these two things become actually dependent, right? So we can only basically say D independent of B given A, but you cannot include C, right? Therefore, just by a counter example, this one isn't encoded in this graph. And you can check the same thing for this one, and I bet you that this statement isn't actually encoded in here either, right? So now, okay, so what's the catch in here? Well, no direct graph model can capture this particular set of conditional independencies. And then we have two attitudes. Suppose that we have this big family of distribution, and we can say that, okay, there are maybe some distributions which can be captured by a graph, and some cannot. That's basically attitude. Okay, we just deal with those ones which can be represented, but for those cannot be represented by a graph, we just live with it. We can just play with a pure number, write down a P of A, B, C, D, and do whatever in the manipulation. That's one thing. But the truth is that this type of distributions is actually a very large family, in the sense that this particular space is also rather big. Without a graphical assistant, you actually lose a lot of power in manipulating probabilistic multivariate distributions. And it actually turns out if you actually want to make use of a different type of graph and invent a new set of conventions in encoding conditional independencies, you actually can also get a good chunk of this part also represented. Okay, so that's basically the topic we're going to cover today, which is a undirected graph model, which is also known as the Markov field. So in this graph, turns out that these two kinds of conditional independencies can be exactly captured in here. Okay, I'm going to tell you, how the conditional independence statement can be extracted from this graph. Of course, on the other hand, this graph cannot capture some other sets of independencies that can be captured here but not there. But that's the story we're going to learn about later.
I have a question.
Yes?
What about partially directed graphical models? Could you build some which are able to encode things get the best of both worlds?
We're going to actually mention a few words later. Yeah, you actually could get the best part of both sides, but they are not necessarily completely overlapping or exhaust the whole space. But anyway, there are ways to combine that. Okay. 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 So that's a summary. So basically, if you only resort to a minimum map, it is far from guaranteed that G will capture the independent statements. But if you want to find a P map, then you can probably find that up to a I equivalence, which I just mentioned. All right, so here is our beginning slice of the undirected graph model. And, very apparently, it is based on a graph whose edges are not having a directionality. Therefore, there is no error on the graph. And usually, the graph captures at a very high level some kind of pairwise relationships between the random variables. But in here, because they are unidirectional, these kind of relationships are symmetric. They are not causal. Say one causes the other. It is hard to make these kind of statements. And such kind of relationship can be very common, actually, in real life, as I'm going to give you a few examples. And then there are rules to tease out the kind of conditional independencies from this graph, and also there are rules to turn the graph into a numerically explicit distribution, as we will see in a second. So here is an example, right? So the example began like this. Here I'm trying to motivate a utility of such a model. So look at a inference problem. So here I give you a block, and with color and other maybe texture and other informations. Now I want to do the inference problem. I asked you whether this is water or air. right? So this is an example I used quite a few times. For those who knows, you probably can tell, but for those who haven't seen this example, can you give me a guess whether it is water or air? Water. Yeah, it's quite blue, right? Yeah, so it's actually quite likely that you'll reach to this conclusion. But what if, I put this in a context? Well, it is indeed water, but on the other hand, if you look at the location of this color in here, it also could be a sky, because it is quite high in the picture, right? So what are the necessary tools that makes you less likely to make a wrong reasoning, in this context? For example, why you conclude that even though this square is high above in the picture, you still want to conclude it is a water? The nearby one is a land. Okay. Okay, so basically what I hear is that you really want to look at the context of this picture and try to see what are the nearby regions should be labeled, right? All right, so probabilistically, that translates to perhaps the following inference problem. Maybe this graph should really be cut into, different, into a grid. And for each grid, you basically put there a label, and it should be labeled with either water or land or sky or stuff like that. And also you want the inference outcome on each different nodes to be somewhat interdependent, right? What can we mean by interdependent? Maybe there is a tendency that adjacent nodes should be labeled in a similar fashion rather than completely independent or opposite, right? That's a possible guess. Of course, in this particular two pair, you'll see an opposite labeling, but in most of the places, you will see pretty contiguous labeling of the grid, right? So that pretty much gives you, a structural information that defines the coupling between different random variables. But this coupling is not a causal one. It is not like this one causes that or the other one causes the other. It's really a symmetric influence. Right. So that model I just talked about actually can be captured by a probabilistic distribution known as the grid model or the Ising model, in which every node now is defined as a random variable, and then they will take certain values, either a discrete value of the content they should be labeled with, or the features that is observed in that thing. But the highlight of this model, the essence of this model is really that the random variable should be interdependent, as captured in this graph. Okay, so undirected graph model is really making use of this graphical, topology to formulate the interdependencies between random variables. I have a few other examples. Here is the network you saw before. I don't know, for some reason the edges are still missing, but it is a social network. If you want to write a probabilistic distribution, again, you can use this graph to define a plausible distribution. And undirected graph model are used in many places because most of the graph, maybe not most, but at least a good fraction of the natural graph that you encountered in real life are actually undirected. So here is another example. It is encountered in biology where people study protein-protein interaction. And by definition, this kind of protein-protein interaction is discovered by doing a type of experiment known as the Is2 hybrid experiment, where basically people glue the two proteins together in an artificial system to see they actually create a response or not. And the way they got glued together isn't anything asymmetric. They just happen to stay together in a single cell. Therefore, all the interactions between a pair of proteins is discovered as unidirectional. And here is another example. People want to play a complicated game like Go, for example. And you can imagine, these different seeds here are random variables. And you can basically define your variables to be white and black. And where to put your next move, of course, depend on the move you made before. Therefore, that's also a interdependent action that you have to make. And recently, there are newer applications in information retrieval and other domain where people can define even more complicated random variables. For example, here is actually this is a model which got a lot of attention these days, which is, it's called the restricted Boltzmann machine, a fancy name. It is the building block of the so-called deep neural network people are using now for discovering complex signals from complicated input data. And here is just one example of a layer of that deep network in which in the bottom of the network you have all these different data, image and text. And one level above that you have latent variables which may define latent topics or latent features that are supposedly generating or maybe relating to the actual data you observed. Right? So all these models have this common feature that the edges connecting different nodes are undirected. Therefore, you can use the very generic notion of undirected graph model to define a distribution on that. So with that, let's start with maybe a slightly deeper mathematical dive into how such distribution can be defined. So the definition is actually quite simple. You have a graph, and we assume that on the graph, we are going to define a set of functions called potential functions, okay, for the cliques in the graph. Okay, so for every graph, you can always find clique structures on the graph. What is a clique?
A subset of nodes where every node is connected to the other.
Yes, okay. And if you treat that as the unit of a graph, then for every one of that, you need to define a potential function, and then you simply multiply all these cliques together, okay? And I'm going to discuss more about how to numerically define the clique function, but as of now, let's assume that these clique functions are rather flexible. They does not have to be a probabilistic table that sum to 1. They can be any so-called pre-probabilistic score. For example, if two labels, are likely to be similar, I give them, a coupling strength of 10, for example, and otherwise I give them a coupling strength of minus 10 or whatever, or 5 or stuff like that. You can put any number there, but at the end of the day, the consequence is that after you multiply all this, they do not give you a probability 1. Therefore, I need to have a partition function z, which is computed by summing over all the possible assignments you can have for this big product of potential functions. And then you divide this product by that. That guarantees you a probabilistic distribution. Clear about that? Okay, so this is a very simple definition. Of course, this very existence of the z function is going to give you a lot of trouble, as we'll study later. But now let's just assume that it is somehow given, and then you have a properly defined distribution. This distribution is known as a Markov random field. Sometimes it is also called a Markov network. And for that, now we're clear that we need to have two components to define a distribution. One is the graph itself, and the other is the potential functions that we need to define on every graph cliques. And now let's study each of them one by one. Okay. First, let's take a little bit, a little deeper look into the graph topology and their semantic meanings. Okay, like what we did for the direct graph model. So for every graph, we actually want it to represent the set of conditional independence properties, right? And the set of independence properties on a undirected graph is actually easier to be described than the direct graph model. So here is the definition. Basically, again, given three sets, we set A is independent of set C given B if set B graphically separates A and C. Okay, very, very direct definition. There is no D separation, no moralized graph, no ancestral graph, just the original graph. And if you see a graph separation, that defines a conditional independencies. Therefore, for every graph, you can now easily extract this set of conditional independencies. Okay, that's why in the earlier example, remember we want A independent of B given C and D, and C independent of D given A and B. We said that this particular graphic model can be very safe. Because if you apply this rule, you actually get exactly this set of independencies. Okay? And this particular statement is good for you to discover all the global Markov independencies, because you can basically apply these three sets to any arbitrary subset on the graph, whether they are adjacent or not. Okay, so that gives you the global property. And sometimes, for various reasons, people care about the so-called local Markov independencies. For example, when we later learn an algorithm called Gibbs sampling, we actually want to know the set of variables which is conditionally independent of a particular given random variable. Okay, and in that case, the local notion is more important and practically useful. And in this case, the definition of the local Markov independency is also very easy. Remember our definition of the Markov blanket in Bayesian network? What is the Markov blanket in a Bayesian network? Say I have a random variable here. What is his Markov blanket? Children and parents of children, yes. So it's kind of a cumbersome to write the Markov blanket of a Bayesian network, of a node in a Bayesian network. But for a Markov random field, it is very easy. Okay, it is just the graphical neighborhood of this particular node. There is no direction here. That's the Markov blanket. Therefore, we have this set of conditional independence properties. Every random variable is conditionally independent of its non-Markov blanket, given its Markov blanket. Okay. And here is a graphical illustration of that. Okay, you can see that the neighborhood of this graph directly isolates the node from the rest of the graph. All right. So that's the conditional independence properties encoded in the graph, which completes the qualitative description of a graphic model. Now let's get more quantitative. So as I said, there is a need for defining potential functions on the cliques in the graph. And let's take a closer look of these cliques. In fact, for every given graph, there are lots of different cliques, right? For example, in here, this is a 4-node graph. And what are the cliques? Well, here I already said, this is a clique, right? And this is a clique. And every edge also generates a clique. And every node itself is a clique, right? So for which set of cliques I should define a potential function? Okay, so that's a question we need to ask. And also, what makes the difference, if we define the potential functions on different subsets of cliques? Okay, so for convenience, let's give some names for the cliques. There are the bigger cliques, which we call the max clique, which means that if you add one more node into that clique, it stops being a clique. Okay, that's the max clique. And there are subcliques, which is the cliques that is a subset of the max clique. And they actually happen to represent two different kind of styles of parameterizing a Markov random field. Okay, And so as just recall, we need to define a potential function on every clique, and now let's see what this clique actually mean, potential function actually mean. So say we have here a network of 3 nodes, and usually a clique function is just a table. For example, here I have 2 cliques, right? I have 2 cliques, and a potential function on a clique is a little bit different from a distribution on a set of random variables, because in here we don't need a probabilistic qualification of the numbers. For example, here I can write down a number, a table, x and y, and again, suppose they are binary discrete. I have 1, 1, 0, 1, 1, 0, and 0, 0. And just imagine, this is person A, and this is person B, just say 2 nodes in a social network. And I just want to, define the clique function in a very, very intuitive fashion. If person A and B are doing the same thing, I encourage them with a score of 10. And if they do opposite thing, I give them no credit. And if one of them is doing the thing I want, I give them a half credit or something like that. Okay, so that's basically a definition of the clique. So more rigorously, the only requirement for you to define a valid clique function is that all the numbers must be non-negative. Why?
So that they can eventually define a probability distribution?
Yeah, because if you multiply them together and there is a negative number somewhere, then the whole thing becomes negative, and you'll stop getting probability, no matter how you normalize the distribution, right? All right, that's one thing. Of course, nothing prevents you from putting probabilistic number here. Okay, you still can put the number here to be normalized. That's fine, but it gives you more flexibility in case you don't want to do that. So now it's interesting to ask what this table probabilistically mean. Okay, if we do a number here, certainly it is not a probability, and or maybe I just want to force myself to make it a probabilistic table. Can I do that for all the potential functions? Or is there a one-to-one correspondence between a potential function and a specific probabilistic entity, in my distribution? Well, the answer is that it is not true. Okay, so for example, just by giving you an example like this, I have a 3-variable distribution, and I can always decouple this like this. This is just a chain rule, right? And using the graphical topology. And now, because here I have only 2 potential functions, right? So here I have a p of x and y, and the phi of y and z. Then there are only 3 pieces here. If I want to group them into 2 pieces to make each one correspond to a potential, I can either group them this way or group them that way, right? And then these 2 must be each correspond to a potential function. Now the strange thing happens. This potential function is a joint distribution of x and y, and that potential function is a conditional distribution of z given y, right? So the potential function can be either a joint or a conditional. And likewise, in this decomposition, you have the same thing. So what I'm saying is that the potential function is more flexible, than just a single probabilistic entity. They can be different probabilistic entity, or they can be no probabilistic at all, just like the table in here. Okay, and that's actually one reason people, in many cases, like a potential-based definition of a graphic model, because it gives you a lot of flexibility. And okay, so why such a? Can you imagine a scenario where such probability is needed? Why people sometimes cannot live with a directed notion where, I need to put a number, in a pairwise potential function, for example.
For example, if you are looking at two variables and how often they appear together in a corpus, you may just want to associate a count rather than a probability distribution over that.
Yeah, that could be a very good scenario. The very first origin of this kind of model actually came from the physics world. Okay, in the 30s, when people studied the atomic structure, they want to define the likelihood of an energy state, and their subject for modeling is a collection of atoms, right? And so if you see a pair of atoms, and you want to describe their energy state, of course, that state depends on the spin configuration of every atom, right? One atom had either a positive spin or a negative spin, and physicists used to call them +1 and -1. And then you put a potential, like we do here, and then if they are parallel or if they are anti-parallel, you want to give them a tendency of overall existence. It's very hard to assign a probabilistic number in that case, right? Usually you have some indirect measure, and also giving them the local normalized assignment isn't necessarily getting a lot of how should I say that? It is actually reducing the power of the model. Why? So if, for example, a pair of atoms like in this particular potential function is already self-normalizing, okay, depending on their forced state configurations, they sum to 1, then they actually cannot be influenced by additional state outside of this pair because they are self-normalizable, right? So in a sense, every pair in here will contribute equally to the overall state of the end of the piece of metal or entity. And I will see in the future, there was this famous model called conditional random field, which actually illustrates that such an idea is not very good because there are some long-term dependencies, okay, so that you don't want every local state to self-normalize because they have to trade off with other states to see a global alignment of all states to create a favorable states. I know this is very abstract, but just keep in your mind that there is a potential increase of power, by using a potential-based representation of distribution. All right, so now let's examine more closely how numerically they look like. Okay, so this is a 4-variable macro-random field, and we can first do the very canonical way of parameterizing. We identify the two cliques in this graphical model, and these are the two cliques. Okay, so very simple. You just build two, 3-dimensional tables and put the right numbers there. You can put arbitrary numbers here if you actually want to design by yourself, or you can learn the numbers if you have enough data and optimize certain loss function. And that's pretty much a way of representing this particular distribution. And you can multiply them together, and then each of these particular phi will be picking up one of the possible entries in this table and gets you a number, right? And once they are properly normalized by z, that gives you the likelihood of a particular state of this 4-variable domain. Okay. And you can probably already observe that computing this z, if you're not given, is not very easy, right? Because you need to sum over all possible configurations, okay? And this is actually, one of the biggest challenge in probabilistic inference. Computing partition function still remains an open problem. It's only doable for certain models. And we're going to discuss later how can we solve the z function for certain cases. Another way of parameterizing the UGM is to use the subcliques. Okay, so by the way, I call this fully parameterized, complete maxi-clique based representation P prime. That's one way of parameterizing. I have P double prime, which is based on definitions on only the subcliques, the pairwise cliques. Okay. So in here, you need to have now 5 tables. Each of them is a 2-dimensional table to parameterize the whole thing. So you may need to deal with a few more terms, but you may have an easy life in creating this number because putting the configuration of a pair is always easier than putting the configuration of a triplet. Right. All right. So now do you have any questions regarding these 2 ways of representing the distribution? Are they equivalent? Why actually, which way should I prefer, for example? Mm-hmm. Yes?
What about cliques with just individual variables? You never use those in representation?
You can do that as well. Yeah. But usually we don't do that. In fact, if you do that, you cannot really capture any structure in a graph, right? Because the edges are not even captured. Yeah. So when we say subclique and the subclique, we usually don't include the singleton nodes. Yeah. Any other comments? Let me ask this. So certainly, graphically, the same graph can represent only the same set of distributions, or same set of conditional independencies, right? Because the dependencies is intrinsic with the graph topology itself. Now I use such a rule to define a distribution on that. Therefore, I also have the I sets for 2 distributions. Now I ask, are they equivalent or not? Any suggestions? And also, I have another question. There are different ways of parameterizing the table and the cube. And therefore, the different ways of parameterizing defines a family of such distributions. And I ask, are these 2 families the same size or not?
For independence, they should be the same because it only depends on graphically being separated, the sets.
Mm-hmm.
So it should be the same.
Okay. I like that answer. You are right, they are the same because the way I write down this is completely motivated by the same graph. And I allow arbitrary parameterization, in the tables, right? And for this, what's that? The max will be smaller than the subcliques. Okay. You are right that they are different, but I don't see why this should be smaller than that one. Because a special case of the max clique is, yeah, right? So for example, one way of defining a max clique is to actually use, the 3 subcliques here, here, and there, right? So this one is indeed bigger than the other one, because all the, ways you can parameterize the 2 variable tables can be also captured in the 3 variable tables, but not vice versa. See that?
Are there any reasons besides computation that one might want to select one way of representation over another conceptually?
Are there what?
Are there any reasons that one might want to choose a max clique representation rather than a subclique?
Yeah, that's a design issue.
Besides computation.
It gives you more power again because you can explicitly capture the 3-way dependencies between the variables, right? Which could be indirectly achieved by the 2-way table, but it's harder. For example, now I want a configuration where the 3 nodes all take 1 should get a better score. And it is not quite easy to achieve that by doing this. It's still achievable, but you need to do more work. So it's really out of a design convenience. People sometimes prefer the other way. But of course, the representation cost is bigger. Right? Yeah?
Can you explain the D prime again? What's
The
the definition of the D prime, the last one? The definition of
Oh, the D is the family of all ways you can parameterize that table. Right? You can put, for example, 10, 10, 0, 0, 11, 11, 2, 2, you know, all these different numbers which are valid. And that basically is the space of your numbers. Right? Yeah. All right. And just for completeness, I can always, have this so-called canonical representation where I put parameterization on all the cliques, both the triplets, the pairs, and the singletons. That's fine. But it gives you the most complete representational power, but at a cost of a heavier burden in the representational cost. And you can work out these relationships by yourself as well. Right. All right. Any questions before I move on to some more specific examples? That finishes basically the basic representation of UGM. And maybe we should summarize with a few high-level theorems. Yeah.
Could you just explain the part on the previous slide, the D of P prime is the previous slide.
Okay.
D of P prime is greater than D of P double prime.
Yeah.
Explain that part again.
Oh, okay. So again, I don't want to give you a very rigorous explanation. It's just like all the way you want to use to parameterize this can be viewed as a special case of that 3-dimensional table. Okay, because the 3-dimensional table, one way of defining the 3-dimensional table is a multiplication of 3 pairs. That's it. Right? But there are some way of defining the 3-dimensional table that can be not decomposed as a multiplication of 3 pairs. Okay, that's my proof, very simple proof. Yeah.
So that will always just be dominated by the largest table in whatever representation.
Yeah, imagine, just imagine the most complete way you do any parameterization is just to write a 4-dimensional table for the whole thing. That covers everything. It's more rich, right? So this is just, but of course in there you don't have a explicit conditional independence automatically realized, right?
So
Yeah.
is the max cliques is the special case of subcliques?
Special case, subcliques are the special cases of the max clique. You never call the superset to be a special case of the subset. Right? The subcliques are a special, defines a family that is a subset of the max cliques. All right? Okay, maybe you should maybe go home and dive into the book and read a little more. I need to move on to finish some more interesting material in the lecture. And the correctness of what I just said, which basically means that a graph in the undirected graph leads to a consistently defined probability distribution, is actually summarized in this theorem called the Hammersley-Clifford theorem. It says that let the distribution to be, actually this is a very important word, a positive distribution over random variables. I will be more explicit in saying what is this. Let P to be such a distribution, and H being a Markov network, okay? And then if, this H is used as a IMAP of P, then P must be a Gibbs distribution over H. Gibbs distribution is exactly this distribution. It's the multiplication of Clique potentials up to a normalization constant. Okay, that pretty much established the equivalence between a graph and a distribution with one subtlety in which we must assume the P to be the so-called positive distribution. If you can remember why we need that kind of clarification. Because we said last time that you can sometimes play with the number to shut off certain conditional independencies or generate certain conditional independence, right, by ignoring configurations of certain random variables. Right? Remember the 2 rows in the table can be identical regardless of their dependent state, then that actually creates a zero probability distribution, and that, of course, generates irregularities in this equivalence. So we exclude that. And okay, so this is how you get the dependencies, and this is, again, the reiteration of the soundness and the correctness proof, right? If you go from H to P, you have this soundness. If your P is always a Gibbs, then you guarantee that H is an IMAP of P. But on the other hand, if you say H is an IMAP of P, you have to make sure that it is a positive distribution. Otherwise, you have only some of those non-positive distributions that satisfy the whole thing. Okay. All right. So I think I have another 30 minutes. Let me skip these few slices of illustration of specific local dependencies and the pairwise dependencies and the global dependencies that you can go home and examine yourself. And that's basically manipulation of the same concept in different scope. And that's not very technical and very difficult. So I'm going to jump to a later set of slides, which kind of give you the global picture, and then we discuss some specific examples of Markov field. So far, we've already see actually two types of graphic models, right? A directed one and an undirected one. And we also mentioned this notion about the perfect map, in which we have an ideal world where the set of independencies in the graph is equivalent to the set of independencies in the graphical model, in a probabilistic model, right? It turns out that neither BaseNet or MRF, can always be a perfect map of any distribution. That's what we learned so far already, right? For example, let's see. Suppose here I have a total family of distributions, and for the kind of a directed graph model, what kind of dependencies in the distribution it can guarantee to capture? Or it cannot capture, for example. So this diamond thing we just studied cannot be captured in here, right? So it must be in somewhere here, right? So it means that there are some probabilistic distributions whose perfect map cannot be in this particular ellipsoid. It must be somewhere here or other places. Right? What are the type of distributions whose independencies cannot be captured by a undirected graph model? The V structures, right? Okay. And what are the stuff which can be captured by both? Maybe something like this. Right? They are about the same. And that gives you the full picture now. We are trying, there actually can be, maybe some additional graphical model which can expand this space a little bit more, but we're not going to discuss that. These are the two main classes of distributions which we usually find useful, but they are not the entire space of all distributions. There are something which is not covered here, and we're not going to discuss this in this class. Okay. All right. So now let's move on a little bit further to see the practical aspects of using Markov fields for our modeling purposes. And before I go there, I want to introduce another new technique, okay, called the exponential form, so that you can just get your life easier. It will increase you any expression power or anything, but it just gives you easy life in designing your models. So we talked about potential functions, and the whole distribution is a product of potentials defined over all cliques, right? And then there is this very strong requirement that all potential functions has to be non-negative. Okay, nothing wrong with that, quite benign, but it does create some inconvenience, right? For example, when physicists were talking about the spin configuration, what do we mean by parallel state getting a score of 10 and the anti-parallel getting a score of 5? It just makes them annoyed because 10 and 5 seems to be very asymmetric, even though the anti-parallel and the parallel states are a very symmetric description of the state of the world, right? They'd rather give, say, one thing gets score 1, the other gets score -1, something like that. So just for this modeling convenience, they invented this so-called energy function, okay, which can be positive or negative. And then to turn the energy function into a potential function, they put a minus sign here for convenience, for a reason has nothing to do with probability. But you will see later on why it is interesting. But anyway, the most important thing is this exponential sign. They exponentiate this energy function so that the outcome is a positive number all the time. Okay, and therefore, with the energy function, my definition of a joint distribution on macro-random field become, the sum of all energy functions over cliques. Okay, and this sum actually gets a name. It is called the free energy of the entire domain of your modeling. And you can see actually this word obviously comes from the physicist, right? And it is actually also called the Boltzmann distribution due to its inventor more than 100 years ago. And in the statistics domain, it is also called a log linear model, okay? Because if you take the logarithm on both sides, you have a linear function to the energy states, okay? All right, so that's one thing I want you to remember because I actually make our life of modeling easy. And here, let's study a few models, okay, defined in this principle. So the first one is the so-called Boltzmann machine, which was actually proposed by the very inventor of this whole formalism. As you know, Boltzmann is a thermophysicist. He was trying to find an equation to model the energy state of gas and of other, physical material. And here is his most basic function, in which he first introduced a graph to capture what he believes to be the interdependencies between atoms. Okay, in here he used a complete graph, but there is nothing preventing you from deleting some edges to make them incomplete. And then he's going to introduce a potential function for every such edge on the graph. So he basically uses the so-called subclique definition. And you can see why subclique here is more convenient. Because he was a physicist, he actually believes that every atom here, with respect to their energy state, spin state, should be described by a random variable. And he wants to make the whole energy function or the whole distribution to be a direct function of this energy of these random variables on every atom. Okay. Therefore, his energy function in here, sometimes this is also called a exponential potential function or potential function. He basically defined this to be the product of the two energy states. Okay, so x1 and x2, and there are some virtues of that because x1 and the x usually takes value from -1 and +1, and if you multiply a pair of x, if they are in the same spin state, regardless of their plus or -1, they should always produce a 1, which means that they are aligned. Otherwise, if they are anti-parallel, they give you a total energy of -1. That's actually the trickiness of designing this particular potential function. And this is known as the Boltzmann machine. Okay, that's a particular way of drawing a graph on the random variables and a particular way of defining the potential functions on the edges. Okay, and in fact, if you do a little bit more work, you will realize that there is some easier, algebraic kind of simplification of writing down this equation, the whole set of the energy can be actually expressed in a very easy matrix multiplication form. And this theta is a matrix of all these weights of pairwise potentials. Okay, I leave this exercise to you if you are curious about how to get from here to here. Okay, it's a very simple algebraic kind of clearance. Okay, that's our first model. And you probably can already see that this model can be quite easily specialized into some particular modeling task. So, for example, here is a Nobel Prize winning model called the Ising model, in which the author uses a particular type of graph structure. So here I have this lattice structure, which is very commonly seen in a solid state metals or salts or stuff like that, right? And he basically ignores the edges, on the diagonal side. And then same thing, same way of parameterizing the potential functions. And I think everything is the same. And this is called the Ising model. And that gives you a function of writing down the total energy of this entire piece of metal, for example. And there are some fancier case, which is known as the Potts model, in which every particular state here is not a binary state anymore. Here it is binary, +1 and -1. You can make them multi-state, say state from 1 to k. Okay. So do you see an example of using a Potts model in our potential modeling task?
Recognizing the sky and the water.
Yeah, exactly, right? That picture has at least more than 2 states. And you pretty much just adopt this Potts model on top of that. Okay. All right. And of course, my favorite example Go is a Ising model. You have black and white state. Actually, it could be also a Potts state, black and white and nothing, right? All right. So now let's these are some new material I just put over the weekend to replace some old stuff. I want you guys to know another model directly inspired by the Boltzmann machine. Okay, it's called the restricted Boltzmann machine, which look like this. It is a asymmetric model. So in the previous model like this, all the nodes, are intrinsically identical in terms of their property, right? They just have different states configuration, but their state space is the same. But in here, I have a heterogeneous domain where I have some orange nodes which are completely observed. They can be, like the sound waves in your speech recognition problem, or the pixel values of your image segmentation problem. And then there is also a collection of so-called the hidden units, which bear some mysterious hidden meaning. Some people, when I actually first play with this model, I call them topics because I want to use this model to, replicate or maybe enhance the function people had in a topic model. We're going to reach that story later when you learn topic models. But in the way that Jeff Hinton, who is the inventor of this model, in the context of his usage, he actually viewed this as a layer in the deep learning network. And they actually produce somehow the hidden features from the real data. And maybe hidden meta features, features of features, for example, of different layers, right? So no matter what, it is something hidden that you have to infer. And the model is written in this way. Again, you have singleton potentials on every node. And that is to translate the actual observed feature into some nice form that you like to deal with. For example, they can be threshold into a particular range. They can be transformed into all positive or anything, right? And they actually receive a weight. These are the singleton weights of every nodal potential. And then, because I also have all these edges, I'm going to introduce the so-called pairwise potential, which defines the dependencies between a hidden state and a observed feature. Maybe using the topic as an example, say this is a topic of sports, some latent representation of topic sports. Say topic sports now take strength 10. Okay, then it needs to influence the value of this particular feature. Maybe a sports picture, for example, in a particular way. They should be strongly coupled or something. Right? So that's why we have the pairwise feature weighted by a particular parameter in here. And then, of course, at the end of the day, this is the log partition function, okay, and to make sure everything become normalizable. So that's basically the design of a restricted Boltzmann machine. So why it is interesting? Well, this is interesting because it can be used, as it is, to actually extract a lot of summarizing information from raw data. So this is raw data. This is potentially a summary of the raw data, different topics. But furthermore, this can be a building block of higher order models, right? There is nothing preventing me from maybe adding some more nodes and do like this, right? And then you actually suddenly see two RBMs, right? This is one, and this is one, and they can basically be used to, extract different levels of features from the raw data. Yeah.
So the second term is not observed.
Oh yeah, nothing is observed up to here, and up above there, no one is observed.
No, even in the first case, in the equation, the second term,
Oh yeah, it is not observed. Yes.
So what do we do then? I mean, how do we learn those parameters?
Yeah, so that's actually, every model basically has, both observed variables and unobserved variables. I just write it here as a placeholder, and down the road we're going to write queries. The query could be P of H given X, and you're going to now solve this problem by doing inference, and that's actually the later lectures. Right now, I'm just telling you how to define a model symbolically on top of all the states I care about, regardless of they are observed or not. Okay. All right, and there's a lot of history about this model. In fact, even the name originally was different. It's called harmonic for some time, and later I actually don't know why it is called a restricted Boltzmann machine. Well, it is a Boltzmann machine. Most of the MRF is a Boltzmann machine, and in this case, it is restricted because the edges are only allowed between the two layers. You shouldn't have edges within the layer. That's why it is called restricted. Okay. And these type of machines are very interesting. And in fact, to answer one of your questions, writing down the inference problem, for example, the conditional distribution of a latent state, okay, given the observed one, can be made very easy using this model. Why? Well, remember that in a Bayesian network, if you remember, we have a lot of V structure, right? Every kind of pair of hidden node plus a observed node is a V. And when we have a V structure, you are in trouble, because that means observing this couples a pair of random variables. Therefore, there are, all these pairwise coupling between the hidden random variables. Therefore, your joint distribution of latent variable given the observation cannot be decoupled. That's a very, very expensive expression. And if you want to, for example, do an inference where P of Li given all the W, that's going to be a very difficult problem, because you have to start from the scratch in here and do some marginalization, right? But in this undirected graph model, which is called RBM, the presence of this actually decouples these two. Therefore, you can write this down as a product of this very simple, single conditional distribution, singleton conditional distributions. Okay. Therefore, once you learn the model, after you pay a lot of cost of learning the model, then doing the inference, deriving the latent value of the feature given observation is a single-step computation. That's also another reason why people like this kind of model. Okay. And of course, easiness in the inference results in easiness in doing, other, probabilistic inference practices. For example, one thing people often do is called the Gibbs sampling for, imputation. And once you have this decoupling, you can make this step rather easy, right? And later on, we're going to cover how to learn this model as well, which also can be made very easy in this particular setting. Another thing, I think I still have a few minutes, is about a clever way of defining these kind of RBMs. I'm not sure it is a direct benefit, but for experienced modelers, they sometimes feel hard to directly write down the full joint based on singleton weights and the pairwise potential weights, because that causes them a loss of power in describing the so-called conditional probabilities. For example, for whatever reason, I want my conditional probability of the hidden nodes given the observed one to be an easy form, maybe a Gaussian distribution, maybe a multinomial distribution, and vice versa. I want my observed one given the hidden to be also a manipulatable easy form, such as a multinomial or something. That's usually what people wanted. Why? Because when they do probabilistic query, what you actually care about is not the joint, it's the conditional like this, or the marginal like this, right? But the way I parameterized this whole thing earlier does not guarantee that. If you write down this whole thing like this, then you actually lose control about the form of a local conditional distribution of a random variable, right? If I want this given that to be a Gaussian, you don't have a way to enforce that in this way. So it turns out that using the RBM kind of model, you can actually define a model in this way, okay? You can begin by writing down the two conditional distribution in the way you want, okay? Gaussian and multinomial maybe. And then you can actually just borrow the original conditional, original potentials in here, okay? And then, add another term, which is a outer product of this potential vector and that potential vector, and weighted by a pairwise score. And then you actually get a joint distribution well defined. And of course here, the weighting theta and the weighting theta here is a little bit different. This is a slightly shifted form of this one, but which can be computed in closed form, can be derived in closed form.
What's
Okay.
the
Yeah.
function of the weight matrix W?
It's just a matrix of numbers that you want to learn. You can put it here as a placeholder. In fact, all these are placeholders. Theta and the theta here are some weights that you probably don't know, right? If you know, you just put a matrix of numbers here. But if you don't know, you put it as a placeholder, right? What is more important is how to take care of the potential functions over the variables. And this equation tells you that the potential function used in here and here can be exactly reused in here without doing any change. Okay. So maybe give you one more concrete example. So here is a definition people use to define where I think it is roughly a information retrieval project where in here. Suppose you want to say these topics given the words is a Gaussian distribution, and these words given topic is a binomial distribution, just the counts of the word frequency. Okay, you just write this down in this way, which is a very natural design. Then you can massage, the parameters like in the way I put it here. I'm not going to explain these equations. It's kind of complicated to tell you how to compute the shift of the rate parameterization against the previous parameterization in the joint distribution form. And then you can pretty much write down this whole thing without too much pain. Okay, you basically reuse the potential function in here, which is the W and the X here, as it is. Okay, so I think people get lost a little bit in here. Let me repeat the message. The message is that if you are given, the data and the definition of the variables you care about, and you want to define a RBM on that, you begin by writing down in your kind of preference the conditional distribution of the data given the latent states and the latent states given the data in these two convenient form that you prefer. And then you can analytically derive, the value of the parameters in this joint distribution of the hidden and the observed variable under a RBM. Okay, the potential functions used in this joint distribution can be directly obtained from the way you define your conditional, and the weights can be calculated in a closed form. That's the high-level message. And for the details, you can actually read the papers that is put on the website as the reading material. And there are equations telling you how to do that. Okay? All right. And I have a few minutes for the last model. That's another very famous macro-random field, which we will spend more time later. It is called the conditional random field. In this case, there are in certain NLP and a certain applied domain in which people want to infer the sequence of a collection of labeling states. For example, here I have a sequence of a sentence with words, and I want to generate the part of speech labels of every word, right? And again, the part of speech labeling is such one that is dependent of each other, right? And then in certain domain, people want to model it as a random field in which there isn't a directionality between the adjacent states. Again, I'm going to be more explicit when we actually study this model, but here I just want to show you the graphical language of capturing this model. So here, you write down a graph like this, and then you put down, now a conditional distribution rather than a joint distribution, because here you only care about the joint distribution over the hidden states, not the observed one. In RBM, you actually are modeling both jointly. In here, you model only the hidden states. And the way you do that is, again, to make use of a collection of potential functions. And in this case, there are two sets of potential functions. Okay, one set of potential function is those defined on the edges. So every edge here gets a potential function, which tells you how coupled a pair of states should be. Okay, maybe labeling this as a noun, this as a verb, this as a noun, is more likely than a verb followed by a verb, something like that. And then you also have the singleton states defined on every node. And then you weight them appropriately, and you add them together, and you get the joint distribution entirely. Okay, so that's a typical way of writing down the macro-random field. And there are a lot of tricks and different techniques of designing these different features, which we are going to actually discuss later when we actually study this model and this inference problem. And at the end of the day, of course, you need to also properly normalize the distribution so that they can be called a probabilistic function.
So why do we want to have the conditional here and the joint in the RBM?
Why that?
Yeah, why?
Good question. You need to really ask the inventor of that. There is a need, which, let's see, it's actually a very good question. In fact, the key notion here is not about being conditional or being joint. The CRF actually, if you look at this model, the main difference is you could actually call this joint, because now I treat X as a feature in my problem. Therefore, I don't actually model its likelihood explicitly. Okay, that's the one reason. But the other reason why this model is different from RBM is that you look at the edge. Okay, yeah, it is actually encouraging explicitly using edge to connect different hidden variables. That's why it is a different model. But yeah, why I use conditional? Because I don't care modeling the likelihood of data. I'm more interested in doing the inference in this case.
But since the features in RBMs are not connected, there you want to model the likelihood of the data.
What's that?
registers in the RBM are not connected, the hidden variables. That's why you want to have the joint.
Okay, it just occurred to me I have a better reason to do that. So it actually, that's my pure guess. I couldn't actually speak for Hinton and John Lafferty, who are the inventors, but here's my guess. So in RBM, the kind of applications is about feature extraction and the latent space modeling. Your training data is only the feature itself, or it's only the data itself, right? Therefore, when you learn the model, you have to maximize the likelihood of observing that data. You have no choice but to do that, right? In here, it is about training a model which do parsing. Your training data actually contain both this and that. It's always safer to make use of the key information that you care about. And in here, you can now define the likelihood only based on the sequence given the data. Therefore, that enables you a new way of training the model, okay, which is in the supervised training domain. And supervised training is always better than unsupervised training if you have the supervision. I bet if you don't have the label, then you no longer need a conditional random field because you don't have a way to train that. That's my guess, but I suspect it is the case. Okay. All right. I think I'm at the end of my lecture today. So here are the high-level notions you want to take home, and basically keep in your mind the differences between the representational power in terms of independencies between the direct model and the undirected model, and then learn how to actually parameterize different type of potential functions depending on your needs in the real data. Okay, and of course these are the 3 interesting models you probably will find useful in your real life problems. All right, thanks.